Okay, picture this. You need to shape a piece of metal, but this piece is so incredibly thin, so delicate, that any normal tool, a drill, a cutter, would just completely wreck it. So how do you do it? How do you carve these impossibly intricate parts without ever physically touching them? Well, the answer is this amazing mix of chemistry and engineering.
I mean, it's a genuine puzzle for engineers, right? If you can't push it, you can't cut it, you can't grind it, without the thing warping or cracking or just overheating, what's left? How in the world do you remove material from a surface you can't even apply force to?
And the answer is, well, it's kind of mind-bending. You don't. Instead of trying to force your way through the material, you use a super-controlled chemical reaction to make certain parts of it just dissolve away. You're subtracting, not forcing.
This whole idea has a name, of course, chemical machining, and it just completely flips the script on how we think about making things. It's way less about brute force and much, much more about precision chemistry.
So here's the key thing to wrap your head around. Chemical machining, or chemical milling as it's sometimes called, doesn't cut anything in the traditional sense. It uses a powerful chemical, an etchant, to literally dissolve the exposed metal, turning the solid into metallic salts that just wash right off.
The basic process is actually brilliantly simple. Seriously, think of it like using a stencil and some spray paint. First, you cover up all the parts of the metal that you want to keep with this protective layer, called a maskant. Then, you just dip the whole thing into a chemical bath. The chemical can only eat away at the parts you left exposed, leaving your perfect shape behind when you're done.
And when you compare it to the old way of doing things, the difference is just night and day. Traditional machining is all about force, right? And that creates stress and heat, which can totally ruin delicate parts. But chemical machining, it's a no-touch, no-stress process. You get these perfectly clean, burr-free edges. It's an absolute game changer for those brittle or super thin materials that would just shatter under a conventional cutting tool.
Okay, so that's the big idea. But how does this elegant process actually play out in a factory? What are the key ingredients you need for this kind of, well, invisible cutting? Really, it all comes down to 4 key players. You've got your etchant. That's the acid or alkali that does the heavy lifting. You have the maskant, that tough, rubbery coating that acts like a shield. The whole show happens inside a special temperature-controlled tank. And finally, there's an agitator, which is basically a fancy stirrer, constantly mixing the solution to make sure fresh etchant is always getting to the surface for a nice, even cut.
Now here's a super critical detail. The chemical doesn't just eat straight down. It also eats sideways, a little bit, right under the edge of that protective mask. This is called undercutting. And it's not a flaw. It's actually a predictable part of the process that engineers have to calculate perfectly so they can control it and get the exact dimensions they're looking for.
And that right there, that leads us to where the real art and science of chemical machining comes in. See, it's not just about dunking a piece of metal in a vat of acid. It's a game of incredible precision, a balancing act of fine-tuning all these different variables to get the perfect result.
Engineers have these levers they can pull to control the whole thing. They can adjust the etchant's concentration, make it stronger and it works faster, but you might get a rougher surface. They can change the temperature. Hotter means faster, but go too hot and you risk damaging that protective maskant. And of course, the most obvious one, the longer you leave it in the tank, the deeper the chemical is going to cut. It's a really delicate dance.
So this all sounds pretty high-tech, maybe even a little niche, right? But where do we actually see this stuff being used in the real world? Well, the applications are way more common than you might think, and they are absolutely critical in some of our most advanced industries. Think about aerospace. It's used to shave off just enough material from huge panels on airplane wings to make them lighter without losing any strength. And your phone? Every time you look at a printed circuit board, you're looking at something made with chemical etching. It's also the secret behind making incredibly fine parts, like microscopic meshes and foils, and even for doing really beautiful, intricate decorative engravings.
But, like any powerful tool in the toolbox, chemical machining isn't the perfect solution for everything. It comes with its own very specific set of pros and cons that engineers have to carefully weigh for every single job.
The upsides are just huge. I mean, you get to shape parts with zero stress or heat damage. You can create unbelievably complex patterns on a bunch of surfaces all at the same time. It's an absolute lifesaver for materials that are just too hard or too brittle for normal tools. And hey, you don't have to buy a bunch of expensive drill bits or cutters, which is a nice bonus.
On the flip side, though, it's slow. You're not going to carve a big block of steel this way anytime soon. And of course, you are dealing with some seriously hazardous toxic chemicals. That means very strict safety rules and a very expensive, highly regulated process for getting rid of the used-up etchant.
Oh, and it's really best for shallow cuts, not for drilling super deep holes.
So, all of this leaves us with a really fascinating question to think about. As our technology keeps getting smaller, lighter, and more complex, and as we invent new and more exotic materials to build with, we might just find that our most powerful and sophisticated tools aren't tools at all. They might just be carefully controlled chemical reactions. The future of making things? Well, it might just be invisible.